Let's continue now with statistical hypotheses, which allow us to determine whether there is a statistically significant difference between two groups. The null hypothesis is the hypothesis of no difference. For example, a medically relevant null hypothesis could be that there's no difference in disease occurrence of two groups in which one group has a certain risk factor of interest. That is, there's no association between the disease and the risk factor of interest in the population. The alternative hypothesis is a hypothesis that there is in fact a difference, meaning that there is some association between the disease and the risk factor in the population. One can create a new 2x2 table with the study results on the vertical axis and the reality on the horizontal axis. Are you starting to see a theme here? When in doubt, on a biostatistics question, draw a 2x2 table. Figuring out what goes into each of the grid boxes helps us to define error. Now, let's talk about types of errors when evaluating statistical hypotheses. First, you could end up with a correct result, which means you state that this is an effect, difference, or relationship when one does in fact exist. Alternatively, you could state that there is not an effect, difference, or relationship when none exists. Basically, you got it right. However, type 1 error is incorrectly stating that there is an effect or difference when none exists in reality. In other words, type 1 error occurs when the experiment or alternative hypothesis is mistakenly accepted and the null hypothesis is rejected, when in reality, the null hypothesis is correct. There's always a chance, in any sample population that is randomly assigned to two groups, that one group will have more smokers or mothers or some other factor. So how do we account for this? The probability of making a type 1 error, or alpha, is equal to the p-value in a study. At the very least, you should know that a p-value is typically judged against a preset level of significance, usually 0.05 in most studies. If p is less than 0.05, this means that there's less than a 5% chance that the data will mistakenly show an effect or difference when none exists in reality. So, less than a 5% chance that your sample populations just happen to be assorted in a way that could affect your results and claims. The lower the p-value, the more confident one can be that the populations are, in fact, different. Type 2 error is stating that there is not an effect or difference when one exists in reality. In other words, type 2 error occurs when you fail to reject the null hypothesis, when in fact the null hypothesis is false. The probability of making a type 2 error is denoted by the Greek letter beta. How can you reduce type 2 error? By increasing your sample size, and thus increasing your chances of acquiring a sample population that more closely reflects your population of interest. Can you see that type 2 error is related to the SEM? Right, the increase in sample size reduces SEM and type 2 error. The concept of power is very important in study design. Power is the probability of rejecting the null hypothesis when it is in fact false, or the likelihood of finding a difference if one in fact exists. Power is an aspect of the study itself, describing how good a study is at assessing that which it sets out to assess. As an analogy, one could say that the power of the judicial system is the likelihood of determining a defendant guilty when he or she is in fact guilty. Hence, powerful study is one that has a high likelihood of detecting an effect or difference when one is present. The mathematical definition of power is 1 minus beta, which means that power can also be thought of as the probability of not making a type 2 error. For example, let's say you're flipping a coin. The null hypothesis is that it's a fair coin, with equal probability of coming up heads or tails, and the alternative hypothesis is that heads is favored. If you only flip the coin 10 times, even if 6 are heads and 4 are tails, you don't have enough statistical significance to reject your null hypothesis, because the power of your experiment is too low. If instead you flipped the coin 1,000 times and got 600 heads and 400 tails, now you have enough power to reject the null hypothesis and conclude that this coin does indeed favor heads. Power depends on several different factors. First, if you increase the sample size, you increase the power of the study. You can remember this with the saying, there's power in numbers. Similarly, if the spread of the data decreases, you're more likely to detect a difference if there is one, and therefore the power of your study increases. Second, if you increase the significance level or probability of type 1 error, alpha, you increase the power. There's a trade-off between type 1 error and type 2 error. So, if you're willing to accept a higher probability of type 1 error, you reduce your probability for type 2 error. Since power is defined as 1 minus type 2 error, this effectively increases the power. Finally, as the difference in the mean values between groups or the size of the expected effect increases, it becomes easier to detect a difference, so power will also increase. Whew! Did you get all of that? Let's see with a practice question. Researchers are designing a study to test the hypothesis that a new beta blocker with fewer side effects will decrease the mortality associated with myocardial infarction compared to the standard of care. They want to make sure they don't incorrectly ascribe a difference between the new beta blocker and the standard of care if there isn't one. Which parameter do they want to maximize? Alpha, beta, 1 minus alpha, or power? The correct answer is C. The researchers want to minimize alpha, which is the probability of erroneously detecting a difference when there really is none. Hence, they want to maximize 1 minus alpha. The confidence interval is defined as the range of values in which a specified proportion of repeated sample means would be expected to fall. It's defined as the range encompassing the mean plus minus the z-score times the standard error of the mean. A z-score describes the distance that a particular data point is away from the population mean in terms of standard deviations. There's only a few things you need to know about the confidence interval and the z-score. The 95% confidence interval most commonly used corresponds to a p-value of 0.05. The z-score for the 95% confidence interval is 1.96, whereas the z-score for a 99% confidence interval is 2.58. More importantly, here are the practical applications of the confidence interval that should be remembered. If the 95% confidence interval for a mean difference between two variables includes 0, then there's no significant difference and the null hypothesis should not be rejected. If the 95% confidence interval for the odds ratio or the relative risk includes 1, then the null hypothesis is also not rejected. Finally, if the confidence interval between two groups overlaps, then these groups are not significantly different. It's fairly high yield for the boards and useful for interpreting clinical studies to understand the differences between these three statistical tests. The boards will likely ask about this information by presenting you with a study and asking, what is the most appropriate test to assess this data? The t-test compares the means of two groups. For example, if you are comparing two cohorts based on systolic blood pressure means, use a t-test to determine whether there is a statistically significant difference. The ANOVA test compares the means of 3 or more groups. For example, if you are comparing 5 different cohorts based on systolic blood pressure means, use ANOVA to test for statistical significance. Basically, an ANOVA does the same thing as a t-test, but for larger numbers of groups. Finally, the chi-squared test compares 2 or more percentages or proportions of categorical outcomes, rather than mean values. Use this test when dealing with categorical data that is represented as fractions, proportions, or percentages. For example, the chi-squared test should be useful for comparing the proportion of smokers with lung cancer versus the proportion of non-smokers with lung cancer. If your patient outcomes can be codified as ones or zeros, as in got the disease or didn't, or got better after treatment or didn't, then you should think of using a chi-squared test. Let's do a question. A study is performed to determine the association between statin therapy and rhabdo, which is muscle breakdown. The findings for 1,000 patients are summarized in the table below. What is the best statistical method for assessing the results of this study? Notice that the patients are divided into two groups, statins versus no statin. And the outcome of interest is a categorical variable, rhabdomyolysis or not. Hence, a chi-square test would be the most suitable for determining whether there is a statistically significant association between statin therapy and rhabdo. Don't be fooled into choosing a two-sample t-test just because there are two groups of patients being compared here. The correlation coefficient, R, by definition, is always between -1 and +1. The closer the absolute value of R is to 1, the stronger the correlation between two variables, either in a positive or negative direction. Can you think of examples of both positive and negative correlations? If the correlation between stroke volume and cardiac output is 0.99, then there's a strong positive correlation between them. As stroke volume increases, cardiac output also increases. If the correlation between vascular resistance and blood flow is 0.99, then there's a strong negative correlation between them. As resistance increases, blood flow decreases. Data with an R closer to 0 might look like this. It's important to notice that R describes the fit of the data about the line, not the slope of the line itself. The coefficient of determination is simply the square of the correlation coefficient. When used in the context of a statistical model like linear regression, it represents the proportion of variability in a data set that is accounted for by the model. Values range from 0 to 1. The closer the value is to 1, the better the model fits the data. Which of these graphs would have an R value closest to 1? A, where you can see the data points are all more closely clustered about the line describing the points. C would be an R value closer to -1. Turning to epidemiology now, let's discuss disease prevention. Disease prevention is divided into 3 tiers and can be remembered by the mnemonic PST, which stands for Prevent, Screen, and Treat. Primary disease prevention is aimed at preventing disease occurrence, to decrease both the incidence and the prevalence of disease. Can you think of examples of primary disease prevention? Examples of primary disease prevention include flu vaccines and hand washing. Secondary disease prevention is aimed at early detection of disease to decrease the severity of the disease. Can you think of examples of secondary disease prevention? Examples of secondary disease prevention include screening tests such as pap smears and colonoscopies. Tertiary disease prevention is aimed at reducing the morbidity and mortality stemming from the disease. Can you think of a few examples of tertiary disease prevention? Examples of tertiary disease prevention include most treatments such as chemotherapy or surgery. There's also quaternary disease prevention, where patients are at risk for unnecessary treatment, and so physicians must protect these populations from the risks associated with new interventions. Medicare and Medicaid are federal programs that originated from amendments to the Social Security Act. How might these show up on the boards? It might be buried in a question answer, such as, because the patient has Medicare insurance, you should offer them blah blah blah. Basically, this will always be the wrong answer, because you should offer the patient all of their options, no matter what their insurance is. Medicare is available to patients over 65 years of age. But if you're less than 65 years of age, you can also get Medicare with certain disabilities, or if you have end-stage renal disease. There are 4 parts to Medicare that you should know about. A is for hospital admission coverage. B is the basic medical bills. Part C is a combination of A and B, where hospital admissions and basic bills are covered by a private company. This is also called Medicare Advantage. Some plans also include Part D, which is for prescription drugs. You can remember these parts pretty easily. A is for admission, B is for bills, and C is for a combo, and D is for drugs. In comparison, Medicaid is federal and state health assistance for people with very low incomes. You should remember that Medicaid coverage and reimbursements differ from state to state, and again, that insurance should never affect the medical advice you give a patient. Just remember that Medicare is for the elderly, and Medicaid is for the destitute. Alright, that's a wrap for epidemiology and biostats. Congratulations!